Thank you, Gabriele, for this introduction. The topic of this series of lectures will be constraints on neutrinos, in particular on the masses, on the mixing angle, and on the decays of neutrinos, and in particular constraints that are coming from particle physics, cosmology, and astrophysics. And when I say particle physics, I mean both theoretical considerations, but quite general theoretical consideration, not specific, detailed, speculative models, and experimental results, direct experimental results from neutrino physics, but also experimental results from other fields of particle physics, which can be related by simple theoretical argument to properties of neutrinos. Of course, in cosmology and astrophysics, also the arguments are coming from both theory and experiment, but in cosmology, the main experiment is the Big Bang itself, and in astrophysics, well, there are also terrestrial experiments. As Gabriele said, I gave about a month ago a theoretical seminar which was discussing basically the same issues. What I would propose to do now in the next 3 lectures, today, tomorrow, and on Friday, is to give a much more detailed and also more pedagogical review of the same subject, adding several important points, mostly fundamental points, which I did not cover in my theoretical seminar a month ago. The topics that I would like to discuss, not all of them at the same detail and not all of them I will devote the same time to, would be, first of all, the introduction of neutrino masses in the general theoretical framework, discussing Dirac masses and Majorana masses. I will then introduce the seesaw mechanism, which is perhaps the most interesting and the most exciting simple theoretical explanation for the fact that neutrinos have very, very tiny masses, if they indeed have masses at all. I will then discuss some theoretical speculations on the mass ratios of the neutrinos. We don't know what are the masses of the neutrinos, but we perhaps have some hints about the mass ratios. I will then move to direct experimental measurements of neutrinos and the bounds which follow from them. And then I will move to the cosmological part of the lectures. First of all, discuss cosmological bounds for stable neutrinos, if neutrinos are stable. I will then move on to cosmological bounds for unstable neutrinos, because, as I will argue, probably all the neutrinos except one are unstable. Once we discuss cosmological bounds on unstable neutrinos, and we declare that neutrinos are unstable, it becomes important to study the possible decay modes of neutrinos, and that will be the next subject, neutrino decays, and how we can derive from an analysis of neutrino decays bounds on masses and lifetimes of the neutrinos. And then we will combine those bounds with the cosmological bounds to derive unified information on neutrino masses and lifetimes. I will then say a few words about the cosmological dark matter of the universe and its possible relation to neutrinos and neutrino masses. That will become later a very important subject. And then move to the mixing angles of the 3 different neutrinos, the 3 different generations of neutrinos, nu e, nu mu, nu tau. I will introduce neutrino oscillations in vacuum and review very briefly the measurements in reactor physics, accelerator physics, and also some information on neutrino mixing from neutrino decays. I will then discuss neutrino oscillations in matter and the Mikheyev-Smirnov-Wolfenstein effect, and review the solar neutrino results, which, of course, can be interpreted in the context of the MSW effect. Once we reach this stage, we will have collected all the information from astrophysics, from cosmology, and from particle physics on neutrino masses and lifetime and mixing, and it will be time to summarize and to discuss different possible scenarios and different possible mass ranges for the neutrinos. And we will see that there are several possibilities, but one of them is particularly exciting and particularly enticing, And I would like to dwell a little bit on that one, and then discuss briefly a few theoretical problems which I find of interest and which I believe we should devote a lot of attention to. And finally, probably the last half of the last lecture will be devoted entirely to future experiments which will be able to test all of these things. Now, this is the plan for the entire 3 lectures, and today I would like to go through the masses, through the cosmology, and depending on time, to get into the subject of neutrino decays. Tomorrow, we will probably conclude the matter of neutrino decays and devote the entire rest of the lecture to oscillations, including solar neutrinos. And then Friday will be the overall view, the discussion of the different aspects, how they play with each other, different scenarios, and the open theoretical problems. Most important, the experiments. So this is the general plan. And you realize, of course, that it is not possible to cover all of this thoroughly in only 3 hours, so I'll have to make shortcuts here and there, but we'll try to be as pedagogical as I can. The whole set of lectures will happen in this playground, to which we will return again and again. And what you have here is the allowed reasonable range for the masses of neutrinos, starting from a microelectron volt, 10 to the minus 6 electron volt, milli-electron volt, electron volt, keV, MeV, GeV. So that particular picture spans 15 orders of magnitude, but of course we could have neutrinos which are much heavier, and definitely we could have neutrinos which are much lighter. And then what you have here are 2 different pictures. On the right, you have a graph of the mass of the neutrino versus the lifetime of neutrino. And again, the lifetime starts at about 1 second and ends on this particular picture with the age of the universe, which is between 10 and 15 giga-years. You have here 1 year just to guide the eyes. And then on the other side, you have an entirely different graph, which is the masses of neutrino versus the mixing angles between the different generations of neutrino, between the E and mu, between the mu and tau, and between the E and tau neutrino. There are 3 different mixing angles. And as I will discuss later, there are actually more than 3. Life is more complicated in the neutrino sector than it is in the quark sector. Here we don't plot the angle and not the sine of the angle, but sine squared 2 theta for reasons that will become clear. Sine squared 2 theta is the number that you measure in oscillation experiments. So what you have here is sine squared 2 theta, where theta is a mixing angle between generations of neutrinos. And just to guide the eyes, you have here the sine squared 2 theta values of the 3 known mixing angles from the quark sector. This need not have anything to do with neutrinos, but they are here just to tell you where the only mixing angles that we have already measured in another different part of physics, where they are, so that perhaps in the neutrino sector they are not too far away from here. The different topics that I discussed will cover this plot in this way, more or less. The cosmology and the decays are correlating the masses and the lifetime and will influence what happens here. If neutrinos are the dark matter of the universe, it means that they have masses between 10 and 100 electron volt, which means that the location is here. The direct experimental limit on the direct measurements of neutrino masses for nu tau, nu mu, and nu e are respectively at these values. All of this I will discuss in great detail. Neutrino oscillations, of course, are related to the mixing angles, and the available data on oscillations in vacuum covers this area, starting at 1/10 of an electron volt and going up. And the available data on solar oscillations probes lower values all the way down to about 100 microelectron volt, about 10 to the minus 4 electron volt, and covers this area. So what will happen is that today's lecture will mostly take place in this area here. We will discuss cosmology, decays, dark matter, and direct measurements. Tomorrow's lecture will take part mostly here. Today's lecture will be on the right-hand picture. Tomorrow's lecture will be on the left-hand picture. And what I really would like to do is to spend all the hour today on showing you why this entire region above this area here is very likely forbidden and excluded. And once we exclude that region and we concentrate our attention below that line, tomorrow we will see what we already can learn about this area, and then we will see why the next important set of experiments has to probe this area, and we will see what to do about it on the third lecture. So with that, I conclude the overview and the general introduction of what I would like to do. And I'd like to move on now to some very elementary concepts related to neutrino masses. And before I even get to that, I'd like to remind all of you what we know about fermion masses, general fermion masses, quarks and leptons in the Standard Model. In the Standard Model, as you know, the left-handed quarks and leptons are in doublets, up and down, charm and strange, top and bottom, electron and its neutrino, muon and its neutrino, tau and its neutrino. All of these left-handed particles are doublets. All of the right-handed particles are singlets. And for the time being, I'm ignoring the mixing, which is, of course, very important, but not for the particular issue I'm discussing now. And how is the mass of all of these fermions generated in the Standard Model? We have the famous Higgs particle, which has a Yukawa coupling to a fermion. What it does, it takes a left-handed fermion and converts it to a right-handed fermion through this Yukawa coupling. The coupling constant can be written as lambda phi FL bar FL. I remind you that the left-handed fermion and the right-handed antifermion, which is the antiparticle of the left-handed fermion, these are doublets. And the right-handed fermion and the left-handed antifermions, these are the singlets. And what you have here is a left-handed fermion, which is a doublet, and a right-handed fermion, which is a singlet. The Higgs particle converts a doublet to a singlet, or if you wish, when you write it this way, you have here the antiparticle of the right-handed fermion, which is the left-handed antifermion, and you again have a doublet, a singlet, and a doublet. It is therefore very clear that the only Higgs particle that can couple to FL bar FL, or in other words, the only Higgs particle that can convert an isospin doublet to an isospin singlet must be a doublet by itself if you are writing an SU2 cos U1 invariant interaction in the Standard Model. So the heroes of the story are the doublet left-handed fermions, the singlet right-handed fermions, and the doublet Higgs. And then the doublet Higgs breaks the symmetry by developing a vacuum expectation value. Because it is a doublet, it means that the symmetry is broken once it disappears into the vacuum. The vacuum expectation value is this, and then this term in the Lagrangian is replaced by lambda, vacuum expectation value FL bar FL, and the product of these two numbers is a certain number, and that number is the coefficient of F bar F, and that, of course, is a mass term, which is the mass of the fermion. That is the normal masses of fermions applicable to up, down, charm, strange, top, bottom, electron, muon, and tau. Let us ignore neutrinos for a moment. It is the normal mass. It is called the Dirac mass. These are Dirac particles, and it comes entirely from a Higgs doublet. Could there also be a Higgs triplet? A Higgs triplet could exist in nature, but even if it did exist, it couldn't couple to these particles for the reasons I already explained. But it could couple to the W and the Z, and it could influence the masses of the W and the Z. But we know that the famous ratio MW over MZ equals sine theta W is a ratio which depends on having a Higgs doublet. And if there would be a Higgs triplet, it would perturb this ratio. This ratio is known to be very accurate experimentally, and that puts a strong upper limit on the possible contribution of a Higgs triplet. And therefore, a Higgs triplet either does not exist, most likely, or exists and has a very, very tiny coupling or a very, very tiny vacuum expectation value. So in the first approximation, let us say that it doesn't exist or that it is irrelevant. How about a Higgs singlet? A Higgs singlet is, of course, something that would conserve the entire symmetry of the Standard Model, just by the fact that it is a singlet. So a Higgs singlet is not something that would break the symmetry, is not something that would give masses to the particle, and there is no reason to expect or not to expect Higgs singlets in the standard model, except that if they existed, they would not be responsible normally to given masses, and certainly they will not be able to break the symmetry of the standard model. They will be preserving the symmetry of the standard model. Why I mentioned the Higgs singlet, you will see in a minute. All of this is very elementary, all of this is very standard as far as quarks and charged leptons are concerned. But what happens for the neutrino? Experimentally, the neutrino is either exactly massless or is very light. Because the upper limit of the masses that you see in a minute are orders of magnitude lighter than the masses of any corresponding leptons. The electron neutrino is less than 7 electron volts, while the electron itself is less than 500,000 electron volts. So there is 5 orders of magnitude at least, and probably many more, between the electron neutrino and the electron. And similarly between the tau-neutrino and the tau, etc. So neutrinos are abnormally light. They are much lighter than all the quarks and leptons, and perhaps they are exactly massless. If they are exactly massless, it does not contradict any fundamental principle of nature, but it is also not explained by any fundamental principle, and it's a big mystery. Because for the neutrino to be exactly massless, you require an absolute exact conservation law, which is valid to all order and is accurate to all orders. And we are not aware of such a conservation law unless we simply postulate it, which is possible. There's nothing wrong, nothing illegal about it, and that is still a possibility. But the rest of these 3 lectures will be based on the assumption that no such extra, special, ad hoc, fundamental new symmetry principle exists, and therefore that the neutrino is perhaps not exactly massless, but is very, very light. And that also requires an explanation. This is essentially as puzzling as a massless neutrino would be. And fortunately, we have a very decent and simple explanation why neutrinos and only neutrinos and nobody else should be much lighter than all the other quarks and leptons. And that explanation is the now famous seesaw mechanism, which I now would like to explain. What can we say about masses of neutrinos? The first thing that we say is neutrinos are like any other quarks and leptons, and they do have Dirac masses, which can be generated exactly in the same way that I outlined before for the quarks and for the other leptons, and here it is. You can have a Dirac mass, which is again given by the coupling of a Higgs field to a neutrino and an antineutrino. The left-handed neutrino is a doublet, the antineutrino left-handed is a singlet, and there is a coupling, a Yukawa coupling, and there is the Higgs doublet. It's exactly the same as the Dirac mass of any other quark and lepton. And then the actual mass of the neutrino is given as usual by the vacuum expectation value of the same Higgs particle, which is already known from the masses of the quarks and the leptons, times a Yukawa coupling to the neutrino, which is not known. And we have no idea what this number is, but we know that all the quarks and the leptons of a given generation within 1 or 2 orders of magnitude have the same mass. The electron up and down have masses which differ by 1 order of magnitude. The neutrino, the electron up and down, yes. The muon, charm, and strange also have masses which differ by 1 order of magnitude. And the tau and bottom differ by factor 3. And the top, presumably, is 100 times heavier than the tau, so you have here 2 orders of magnitude. So if we are just using this type of numerology, we would expect neutrinos, which have Dirac masses generated exactly in the same way, to have masses which are, let's say, within an order of magnitude, at most 2 orders of magnitude, from the other friends of their same generations. And therefore, we would expect a Dirac mass from the neutrino, which is approximately equal, which means, let's say, 1 order of magnitude away, to the Dirac mass of the corresponding charged lepton, say within factor 10 or so. And that would be one type of mass for the neutrino, and so far I haven't said anything new. It is completely identical to what happens for other leptons on quarks. But neutrinos and only neutrinos have another feature which nobody else has. Neutrinos are the only fermions which have no electric charge and no other conserved quantum number in the standard model. And therefore, you can write not only a neutrino-antineutrino term which carries no quantum numbers, but you can also write a neutrino-neutrino term. And therefore, you can create a different type of mass term which only neutrinos can have, which is a neutrino-neutrino mass term. That enables us, instead of writing only a nu bar mass term, write a 2x2 matrix with mass terms which are created from nu bar, nu, and nu bar. All of these possibilities are legitimate for neutrinos, and this is a situation which is different from quarks and leptons. Now, I want to emphasize why this is so important, because if we want to explain why the neutrinos and only the neutrinos are so much lighter than everybody else, we have to find something which is true for neutrinos and only for neutrinos, a certain property, a special property which is valid only for them and for nobody else, and that is that property. So now, instead of writing one mass term, I can create a 2x2 mass matrix, which is labeled here by nu and nu bar, and the nu term will be here, the nu bar term will be here, the nu bar term will be here, and the nu bar term will be here, and there will be 4 different mass terms, and now we would like to study all 4 terms one by one and see what happens. So the first one we already studied, it is a normal Dirac mass, there is nothing new about it, and it is roughly of the order of a lepton mass, give or take factor 10. This one would be a term nu left. Now, the nu left is an isospin doublet with the isospin pointing up, because the doublet is nu, an electron, and the nu is the upper component. And when you have nu left, you have 2 doublets. 2 doublets can normally make a triplet or a singlet, but these are 2 doublets, and both of them are the up components of the doublet. And therefore, the only thing they can make is a triplet with the 3rd component of isospin equal to 1. And therefore, the nu left can couple only to a Higgs particle, which itself is an SU2 triplet. Therefore, such a mass term is perfectly allowed, but it can be driven only by a Higgs particle, which I denote by delta sub L, which by itself is a triplet. So the mass term will be some G prime, some new Yukawa coupling, we don't know anything about it, times a Higgs triplet, nu left, and there will be a mass term, and the mass term, which will be a left-handed Majorana mass. This type of mass is called a Majorana mass because this is a property of a Majorana neutrino, a neutrino which is the antiparticle of itself, and therefore it and itself can create a mass term. And it depends on the vacuum expectation value of this Higgs triplet. But we already said in the previous transparencies when we discussed general standard model is that Higgs triplets either do not exist or have very tiny vacuum expectation values, because otherwise they would perturb significantly the mass ratio mw over mz equals sine theta. And therefore this type of thing is either exactly 0 or very tiny for reasons which have nothing to do with neutrinos. And that is why I put here 0, but this 0 should be understood not as an exact 0, but as a very tiny number. This is the Majorana mass for the left-handed neutrino. But the situation is completely different for the Majorana mass of the right-handed neutrino. In other words, there's an entirely different story when you have nu left bar. You can read it now from bottom to top. There is again a Majorana mass here, but instead of nu left, it is nu right. Or if you wish to write the antiparticles, it will be nu bar left. Now what's the difference between this and that? Here you have a doublet and a doublet, which can couple only to a triplet. Here you have a singlet and a singlet, which can couple only to a singlet. So the only way to make a mass term for nu right, or nu bar left, is by coupling them to a Higgs singlet, delta sub r. Can such a singlet exist? The answer is yes. There is no rule and no reason why not. But even more so, if you stop for a moment and you say, the standard model is not the end of physics. it is clear that there is some physics beyond the standard model. It could be grand unification. It could be technicolor. It could be horizontal symmetries. It could be a possible substructure of the quarks and the leptons. It certainly could be supersymmetry. It could be anything. If there is physics beyond the standard model, and if there is symmetry breaking in that physics, that symmetry breaking would come from a Higgs particle that would violate that symmetry, but would conserve the symmetry of the standard model. Therefore, in all such models, there will be Higgs particles, which are singlets of the standard model, and are not singlet of whatever it is that the bigger symmetry does. And therefore, I'm arguing that Higgs singlets not only are allowed, but are essentially absolutely necessary in any theory which goes beyond the standard model and goes to higher symmetry, which are then broken down to the standard model. Now, not every such model will have a Higgs with precisely the properties that we need for that particular mass term. But all I'm arguing is that Higgs singlets, number one, are not forbidden by anything, and number two, actually exist in all theories that go beyond the standard model. And in many such theories, there are exactly Higgs singlets of the type that we need in order to give a mass here. Furthermore, the vacuum expectation value of such Higgses have nothing to do with the mass scale of the standard model. They represent the mass scale of the next physics. If it is grand unification, it would be 10 to the 15 or 10 to the 16 GeV. If it is the Planck scale, it will be 10 to the 19 GeV. And if it is some other scale, it could be less or more. It could be 1 TeV, it could be 1,000,000 TeV. We don't know what it is. But whatever it is likely to be a very large number representing the energy scale of the next physics. So the Majorana mass for the right-handed neutrino, this term, is allowed to exist. It probably exists. And if it exists, it is very likely to be capital M, a very large number of order lambda, where lambda is the energy scale of the new physics beyond the standard model. So we already constructed three numbers of our 2x2 matrix. The last number is very simple because it is just a complex conjugate of this. This was nu bar, and here we need nu bar nu. So the number here will be exactly the same as the number here, and that completes the matrix. And we are now very happy with the result. We have a 2x2 matrix for neutrinos, which has a normal fermion mass here and here. We have a very large unknown number here, and we have a 0 or a very small number here. So schematically speaking, we have normal, very large, very small. And this is the 2x2 matrix which, for the neutrino, replaces the one number which is the Dirac mass for ordinary fermions. I repeat. For the 6 quarks, up, down, charm, strange, and top, bottom, and for the charged lepton, electron, muon, and tau, we have only a Dirac mass. We only have this number. For nu e, nu mu, and nu tau, for each one of them, we have a 2x2 matrix, which has 4 numbers, of which the 2 off-diagonal numbers are normal. And if they were the only ones that existed, neutrinos would have perfectly normal masses like all the other particles. But there are also 2 other numbers, one of them very large and one of them very small. And therefore, the actual physical masses of the neutrinos will have to depend on diagonalizing this matrix. And diagonalizing this matrix, of course, is a trivial exercise, and that is what the seesaw mechanism is all about. Here is the matrix, normal m, large number, small number. And when you diagonalize it, it is very easy to see that one eigenvalue will be of the order of this very large number, capital M, which is order lambda. And the second eigenvalue will be little m squared divided by this large number. The easiest way to see it, of course, is to notice that the determinant is little m squared. Therefore, the product of the 2 eigenvalues have to be little m squared. On the other hand, the trace is capital lambda, and therefore one of them has to be capital lambda. So one has to be capital lambda, and the product is little m squared. Obviously, therefore, one eigenvalue is very, very large, and the other is little m multiplied by little m over big M, which means it is very small and it is much smaller than little m. So we got here a peculiar situation. Instead of having a normal mass, we end up with having two masses, one much larger than normal and one much smaller than normal. And the normal mass is the geometric mean of the two masses. And that is what the seesaw is all about. It's really a logarithmic seesaw. The higher is the value of capital M or lambda, the smaller will be the value of the small neutrino mass. The product of the two eigenvalues is always a normal mass squared. So the normal masses are the geometric mean. But the heavier one is, the lighter will be the other one. And that was a mechanism that was introduced not in full generalities, but in the context of the gun unification theory by Gelman, Ramon, and Slansky, and by Yanagida many years ago. And that is why it is called a seesaw mechanism, because it looks like a seesaw. And it follows that the physical neutrinos for each generation are an admixture of the normal left-handed neutrino and a tiny bit of the right-handed neutrino, and the other one, the heavy guy, is an admixture of almost pure right-handed neutrino, but a tiny bit of the left-handed neutrino. And in that, they also differ from the normal quarks and leptons. Now, all of this story that I told you about, and this 2x2 matrix, is the story that we would have if we had only one generation, if there would be only one type of neutrino, but we have three types of neutrinos. And because we have three types of neutrino, every one of these things is not a number, but is a 3x3 matrix. So for n generations, little m and capital M are n by n matrices. And you can first of all do what is called in the mathematical jargon block diagonalization. In other words, you first of all can diagonalize this matrix to get two zeros in the off diagonal elements, and that gives you a capital M here, and here you have a matrix which is a little m, inverse capital M, little m. That's little m squared over m, but in matrix notation, and therefore the order is important, and that has to be the order. And when you do it, you end up having n light neutrinos and n heavy neutrinos. In this case, it would be 3 light neutrinos, much lighter than normal particles, and 3 heavy neutrinos, much heavier than normal particles. Notice then that life is more complicated. First of all, instead of the quark sector where you have a 3x3 mixing angle, there's a 3x3 mixing matrix. The Kobayashi-Maskawa, the Kabibo-Kobayashi-Maskawa matrix in the quark sector is 3x3. In the neutrino sector, it will be a 6x6 matrix. And it will mix two different things. First of all, it will mix the 3 generations, but it will also mix the light neutrinos with the heavy neutrinos. That mixing experimentally has to be very, very small, but it has all kinds of effects which are non-trivial. In particular, the 3x3 mixing matrix for the 3 generations of neutrinos will not be exactly a unitary matrix. The unitary matrix is the 6x6 matrix. And because a little bit of it leaks to mixing the 3 light neutrinos with the 3 heavy neutrinos, if you look only at the 3x3 mixing matrix of the 3 light neutrino generations, it will be almost unitary, but not exactly unitary. And that will have a few consequences as we go along. So that's where we are in all of this thing. And that leads you to a situation in which you have this normal mass, which is the geometrical mean between the neutrino mass and the scale of the new physics. Here you have a simple gadget. I think some of the students here are too young to know what a slide rule is. You have here a gadget which is almost like a slide rule, which shows you the connection between the neutrino masses. Here are the neutrino masses. We will return to this several times in the last lecture. Here are the neutrino masses starting with 100 MeV, MeV, keV, eV, going all the way to nano-electron volt. Here is the scale of some possible new physics in GeV, where here is 100 GeV, the mass of the W and the Z. Here is where technicolor begins to play. Substructure, if it exists, could be above a few TeV. There could be left-right symmetric particles above a few tens TeV. There could be a horizontal symmetry, symmetries above hundreds of TeV. There could be new physics scale related with axions and Pechek-Quinn symmetry somewhere around 10 to the 12, although this has difficulties and is maybe on the verge of being excluded. There is GAN unification at 10 to the 15 and SUSY GATS not far above it, and the Planck scale. And then here you have the normal masses of the quarks and the leptons on a scale of, here is the electron at half an MeV, the up at a few MeV, the muon at 100 MeV, the tau and the charm at GeV, etc. And the magic formula of the seesaw mechanism tells you that if you know two of these numbers, it determines the third one on a line, because this has to be the geometric mean, and since this is a logarithmic scale, on that scale it is an arithmetic mean. So for instance, if the correct physics is GAN unification, and the relevant lepton is the tau, and you want to know what would be the mass of the tau-neutrino, the tau-neutrino would have to be about 10 to the minus 5 electron volt, because this is the new physics, and this is the normal mass which is related to it, and that's where it comes. On the other hand, if the new physics is GAN unification and the relevant mass is the top mass, they'll end up at a fraction of an electron volt. On the other hand, if you want the neutrino to be, let's say, at 20 electron volts, which is something that we will discuss in great detail, and you want the relevant particle to be the top, you put it at 20 electron volts here, and you put around the mass of the top, which is, let's say, 100 GeV, and you end up with 10 to the 12 GeV, and so on and so forth. So with this little game, knowing the place of the new physics, you can derive the mass of the neutrino, and vice versa. What can you say about the mass matrices of the three generations? And what can you say about mass ratios of neutrinos? Here is this 6 by 6 mass matrix, 0, little m, big M, where little m and big M are 3 by 3 matrices. The little m matrix could simply represent the normal masses of the leptons, Me, Mu, M tau. But in GAN unification theories, what is more relevant to neutrino masses are actually the masses of the up quarks, because the neutrino is the upper lepton. The leptonic doublet is neutrino, electron. The neutrino is the up component, and the electron is the down component. And in GAN unification theories, usually the ratio of the neutrino masses are proportional to the ratio of the upper or the top quark masses. So in the case of some GAN unification theories, this little m would be proportional not to Me, Mu, M tau, but to Mu, Mc, Mt. This could be an equality, or it could be a proportionality, and the proportionality could be with a factor of 10, or 1/10, or maybe 10 to the minus 3. We just don't know. Capital M we also don't know. It has to be roughly of order lambda, where lambda is the new physics. But it could be lambda, lambda, lambda. Or it could be F1 lambda, F2 lambda, F3 lambda, where F1, F2, F3 are unknown Yukawa couplings, which could be perhaps a fraction, maybe a tenth or a hundredth or God knows what. Perhaps they are all the same. Perhaps they are different for each generation. We don't know that. Perhaps they are proportional to the Yukawa couplings of the normal leptons, in which case F1, F2, F3 would have the same ratio as Me, Mu, M tau. And to add confusion, in all of these cases, there are all these little x's which need not be 0. These are all non-vanishing numbers. They are perhaps small, but they are non-vanishing, and therefore you really have to diagonalize these matrices. So to make a long story short, there's a big confusion here. We don't know really much about what's happening. But if little m is like so, and big M is like so, then the ratio m nu e, m nu mu, m nu tau is going to be independent of what's going on here, the ratio itself, and it will be like m e squared to m u squared to m tau squared. If the big M is like so, and the little m is like so, it will be proportional to mu squared to mc squared to mt squared, which is different ratio. And if it is, for instance, something like so, where the f's are proportional to the masses of the e mu tau, this could be square, and this would be linear, and therefore the ratio would be linear, and it will be like me, mu, m tau. So these are very different possibilities, and all the other possibilities that you can think of are more or less in between them. For instance, if you are particularly interested, and we will be, in the ratio nu tau over nu mu, you find that with this possibility, nu tau over nu mu is m tau over mu squared, which is about 300. With this possibility, it is m top over m charm squared, which is about 10,000. And with this possibility, it is m tau over mu, which is about 17, or in round figures, 20. So there's a very wide range of possibilities, but not as wide as the 15 orders of magnitude for neutrino masses that we allow ourselves. And if you want to put this, again, in a graphical way, you will find these are decays, but I specifically and deliberately did not put any absolute scale here, but each line here is another factor 10. If the mu-neutrino is here, the tau-neutrino could be here, or here, or here, or anywhere in this orange area, depending on whether the correct formula is top over charm squared, which is this one, or tau over mu squared, which is this one, or tau over mu, which is this. And similarly here, the electron neutrino over the mu-neutrino could be anywhere in this orange range, depending on whether it is E over mu, or E squared over mu squared, or up squared over charm squared. But in any case, you see that the electron neutrino in all of these cases will be much smaller than the mu-neutrino, and the tau-neutrino will be much heavier than the mu-neutrino, except we don't know by how much. And we will come back to this also in the next few lectures. Let me move on now to direct measurements of neutrino masses. Let us just stop for a moment and see what we have achieved so far. We've introduced a mechanism which explains to us in a nice way why neutrino masses may be very small. We have tied the smallness of the neutrino mass to the largeness of the scale of the new physics. We realized that everything we said could be wrong by 1, 2, 3, 4 orders of magnitude, but perhaps not by 10 orders of magnitude, which is already a success because we started by knowing absolutely nothing. And now we would like to start collecting information from experiment and from theory and go back to the original plot that we had for the neutrino masses. You remember that we started this lecture with this plot that had neutrino masses that could be anywhere over 15 orders of magnitude. And we now begin to try to locate where real physics is on this plot. We started by saying that each of the three neutrinos, nu e, nu mu, nu tau, could be anywhere here. And now we would like to begin limiting ourselves. And the first thing we do, of course, is direct and almost direct measurements. First of all, direct measurements. Direct measurements are done by looking at direct weak decays involving neutrinos and searching for peculiar effects, peculiar phenomena near the endpoint of the spectrum of the outgoing neutrino, which is determined by the spectrum of the outgoing charged particle. In the case of ordinary beta decay, the best number, which was published only a month ago, is a new experiment from the University of Mainz in Germany, 7 electron volt, actually 7.2. There's also an 8 electron volt measurement from Livermore and a 9 electron volt measurement from Los Alamos. So there are already 3 experiments which are giving us results below 10 electron volt, and the best limit is 7 electron volt. In the case of the mu-neutrino, the best number is obtained from pi decay, and it is 270 keV. That number poses some problems. The previous number was 250 keV. There was a remeasurement of the detailed, accurate properties of pion decay, and the number got a little worse, and this has to be done properly and hopefully soon. The tau-neutrino result is coming from the Argus experiment at DAISY, and the present best value is at 31 MeV, again by looking the decay of tau into several pions, and one can hope in the near future to improve it perhaps to 20 MeV, and if a tau factory is ever built, this can be improved all the way down to a few MeV, but nobody knows how to do that directly to better than that. The supernova 87A gave us 19 neutrinos that came to Japan and to the United States, and by the fact that they arrived safely and within a few seconds, we know that the mass of the neutrino, depending on assumption, is less than 10 electron volt or 15 or 8 or 20, depending exactly what you do, but it's an independent confirmation on this. It also gives us a limit on the lifetime. This is wrong. This is the lifetime of the neutrino. Here at CERN, the fact that LEP determined the number of neutrinos to be 3 only means that there are 3 neutrinos below the Z mass, and therefore a fourth neutrino, if it exists, has to be heavier than 45 GeV. So light neutrinos, there are only 3. And a similar result, which is very important, and we will return to it, comes from primordial nucleosynthesis. And there the story is the following. We know how much helium and what is the abundance of other light elements in the universe is. The ratio of helium to hydrogen is very sensitive to the ratio of neutrons to protons. And the ratios of neutrons to protons depends, first of all, on the mass difference between the neutron and the proton, which is one issue, but it also depends in a very sensitive way on the number of species of particles that were present at the moment of decoupling. And that number of species includes the number of neutrinos. In fact, neutrinos are an important component of this, and that is how the number of neutrino species enters in determining the ratio of neutrons to protons, and through it, the helium to hydrogen ratio, and eventually, in a more complicated way, also the abundance of other isotopes. And through that argument, which I will not repeat here, but it's an old argument, one can determine that the total number of neutrino flavors is less than about 3.3 or 3.4, depending whose analysis you consider. But that relates only to light neutrinos, which are much lighter than 1 MeV. If there is one of the neutrinos which is around MeV, which is entirely possible for the tau-neutrino, then this argument changes in a way to which we will return probably tomorrow, and you will see that it gives an additional piece of information. So here's the summary of the direct information. Here is an amplified version of the mass versus lifetime plot. Here is the mass of the neutrino again, microelectron volt, millielectron volt, electron volt, etc. Here is the lifetime from a millisecond to the age of the universe. 1 year is here and 1 second is here. We know from LEP that the fourth neutrino has to be above 45 GeV. The tau neutrino has to be below 31 MeV. The mu neutrino has to be below 270 keV. The electron neutrino has to be below 7 electron volt. And from the fact that the neutrinos of supernova 87A arrived at Earth, they have to be to the right of this, because their arrival gives us a limit, a lower limit on the lifetime, but that limit on the lifetime depends on the mass. So this is the first time that we see here a combined relationship coming, in this case, from astrophysics, on the lifetime and the mass of the neutrino. Give me a mass and I'll give you a limit on the lifetime. Give me a lifetime, I'll give you a limit on the mass. But there is no absolute limit which is following from that type of experimental result. And it is given by a line, a diagonal line on this plot. We will see many more diagonal lines like this as we go along. And that brings us to cosmology. And I will just get into the cosmology and stop, and we will continue tomorrow. What can we say about neutrino masses from cosmology? First of all, one transparency which has nothing to do with neutrinos, and it has to do with the mass density or the energy density of the universe. This is a definition, this is not a statement. The energy density now of the universe is given by the critical density times omega. This is simply a definition of omega. Omega is that parameter which is larger than 1 for a closed universe, namely for a universe that is eventually going to collapse upon itself, is equal to 1 for a flat universe, and is less than 1 for an open universe, a universe that will continue to expand forever. The flat universe, of course, is the boundary between the two possibilities, and that is the possibility which is favored by most theorists. It is favored by the inflationary universe scenario, and personally I would hope, and most theorists will hope, that this is the way the universe behaves, but we don't really know. The critical density is known. It is 3 times the Hubble parameter squared over 8 pi times Newton's constant. The Hubble parameter is usually measured in units of 100 kilometers per second per megaparsec, and in those units we call it little h. So if you put that unit square times 3 over 8 pi g in front, you have omega little h square as an unknown parameter times this number which is fully determined, and this number is 11 kilovolt for every cubic centimeter. So the energy density of the universe today is 11 kilovolt per cubic centimeter times little h squared times omega. What do we know about omega? What do we know about h? Little h we know is about between 0.4 and 1, and we really don't know where it is. There's a lot of dispute among cosmologists and astrophysicists. There's a lot of arguments. Some will swear that it is 0.7, others will swear that it is 0.5. I don't want to get myself into this. Let us just assume that it's between 0.4 and 1. I'm sorry? The little h, it comes from all the different arguments and observations that we have on the rate of expansion of the universe. This is the Hubble parameter which measures the rate in which the universe is expanding. And there are arguments based on gravitation, there are arguments based on counting observed galaxies, there are arguments based on a large variety of different things, and they're giving different results. And there are entire conferences in astrophysics and cosmology which are discussing the values of h, and there are different schools of thoughts about it. I'm not an expert myself. I've been listening to such things. I've been hearing experts swearing that it is between 0.6 and 0.7. I've been hearing other experts swearing that it's between 0.4 and 0.5. I honestly don't know, but it is a safe bet that it is between 0.4 and 1. Omega is equal to 1 if you believe the theoretical prejudice. It is almost certainly less than 2 if you believe very conservative bounds, although there are other bounds saying that it's less than 3. And if you count only the observed ordinary visible matter in the universe, it is probably of the order of 0.1 or possibly even less, because as you know, most matter in the universe seems to be dark and invisible. So we really don't know, but we would assume that it is probably maybe 1 or a good fraction of 1. Omega and h are not entirely independent because the age of the universe also enters into the calculation. And there's a relationship between the age of the universe and little h and omega. And that relationship is different if the universe is matter-dominated, namely most of the energy density of the universe is matter, is rest mass, or if it is radiation-dominated. In other words, if most of the energy density of the universe is radiation or kinetic energy. But in both cases, there is a clear relationship between the age of the universe, little h, and omega. And for the case of matter-dominated universe, which we suspect is the universe in which we live, what is happening is that you have here a plot for an age of the universe of 15 gigayears. Here is h and here is omega. And for omega equal to 1 and an age of the universe of 15 billion years, the value of little h has to be approximately 0.4 if the universe is matter-dominated. And if the age of the universe is about 10 billion years, And again, the universe is matter dominated. The value of h is here. It's about 0.7, and so on and so forth. For any such number, you can calculate omega h squared, and the best number you get if you assume that the universe is 15 billion years matter dominated and omega is equal to 1 is that omega h squared is about 0.2. On the other hand, if you want to be very conservative, you would say that omega h squared is less than about 7, and when the dust, less than 0.7, and then when the dust settles, you find that rho zero, the present energy density of the universe, is probably around 2 kilovolt per cubic centimeters, but certainly less than 7 kilovolt per cubic centimeter. It could be, of course, much smaller. So a conservative limit would be less than 7 kilovolt per cubic centimeters. The best value, if omega is equal 1, would be about 2 kilovolt per cubic centimeter. So far, I didn't say the word neutrino in this transparency, but now I will make the completely trivial observation that if this is the total energy of the universe, the total energy of all the neutrinos has to be less or equal than that. That's certainly not a very profound statement, and it is certainly correct. Now, if we want to learn from this the mass of each neutrino, or an upper limit on the mass of each neutrino, we have to find out how many neutrinos there are in every cubic centimeter. And I will go through this argument and stop. In the early universe, neutrinos, as the universe was cooling, neutrinos decoupled around a temperature of the order of a few MeV. Below such a temperature, the neutrinos are essentially a non-interacting gas. The probability that they meet each other, that they collide with each other, that they do anything to each other because of the weak interaction and because of the low density, that probability is very small. So you can view neutrinos to be essentially a non-interacting gas since that time, assuming that they are stable, assuming that they do not decay, and therefore nothing happens to them. Every neutrino that existed then will continue to exist. And the only thing that happens is that the density is gradually getting smaller because the universe is expanding. The number of such neutrinos is then behaving in a very similar way to the number of photons in the universe. And the number of photons is, of course, the famous microwave background radiation, primordial microwave background radiation, which has been observed and which is historically was the best and the first major evidence for the standard cosmology, standard Big Bang theory. The only problem is that the number of neutrinos per cubic centimeter is not equal to the number of photons, but it is related to it by a certain factor, which happened to be 3/11, and I will not go through the derivation. That factor has to do simply with counting degrees of freedom. You can find it in any textbook on cosmology. And if we know the number of photons, we know the number of neutrinos per cubic centimeter for each flavor of neutrino, each species of neutrinos. We do know that today there are about 400 photons in every cubic centimeters in the universe. That 400 photons per cubic centimeters is related to the 3-degree background radiation, or more precisely 2.7-degree background radiation. And if you multiply 400 by 3/11, you get 110. And therefore, we know that in every cubic centimeter in the universe, there are 110 electron neutrinos, 110 mu-neutrinos, and 110 tau-neutrino, provided that all of them are substantially lighter than an MeV, and that they are stable. Why lighter than an MeV? Because they have to be light particles at the point of decoupling. Why stable? Because otherwise they would decay and disappear. So if they were light at the point of decoupling, lighter than a couple of MeV, and if they are stable, we know that there are 110 of them in every cubic centimeter. What we do not know is how much mass they have. And since we already decided in the previous transparency that the energy density of the universe is about 2 kilovolt per cubic centimeter, all we have to do is divide this by 110, and then we find two things. We find exactly the mass of the neutrino if the neutrino provides us all the energy density of the universe, and we find an upper limit in the case that the neutrino is less than the full, which is a sure thing, that the neutrino certainly is less than the full energy of the universe. And when we do this, we find a conservative upper limit that the mass of the neutrino, if it is stable, has to be below 65 electron volt. And in the case that omega is equal to 1 and the age of the universe is about 15 billion years, the mass of the neutrino has to be less than 20 electron volt. And if the neutrino is the dark matter of the universe, if almost all the mass of the universe is one type of neutrino, then the mass of that neutrino has to be approximately 20 electron volt, or 15 or 25, but the order of magnitude of 20 electron volt. And this is a very remarkable result, and I want you to note that it depends on very few assumptions. It depends on standard Big Bang cosmology. It depends on what we know about the energy density of the universe, which is rather safe. It depends on the statement that neutrinos are lighter than MeV, which they sure are if they are a few electron volts. And it depends on the statement that